Hey guys, today I want to go ahead and deconstruct our recent summative assessment that we had on April 30th, 2020. In particular, I want to go over questions 3A, B, and C that all deal with periodicity or trends on the periodic table. Um, and then from there, I want to take a look at 5C, that is an intermolecular attractive force type question that's comparing butanoic acid to decane. Okay, so let's go ahead and start with question 3A. The directions for this series of questions asked you to account for each of the following observations in terms of atomic theory. So what I've done is I've kind of worked through a delineation as kind of like a perfect answer. And then what we're going to do is we're going to evaluate some student responses and look to determine whether they would or would not really receive credit for their work. Okay. All right, so the first thing I want to do is identify, whenever we talk about trends, the first thing you have to do is identify what the elements in question, like the two species we're going to be looking to compare, what do they have in common and what do they have differently, um, or what is different about them, I should say. And there's really only two things we need to account for. Either they're going to be in the same period, they're going to be in the same row, right? Which means they have the same, as far as like valence electrons, their valence electrons are in the same principal energy level. So what is different about them, what we need to key in on, is their effective nuclear charge, right? So any two elements that are in the same period going like left to right on the periodic table, we're focusing on the difference as far as nuclear charge goes, or effective nuclear charge, since their valence electrons are in the exact same principal energy level. Now, if we're talking about elements or atoms, ions, whatever the case is, that are going to be in the same column, um, then what we need to be talking about is the difference in their principal energy level, right? The fact that the valence electrons are going to be in different separate energy levels, different distances away from nuclei, and per Coulomb's law, obviously that has ramifications, okay? All right, so for this first question here, the electronegativity of bromine is larger than for calcium. I've started by identifying that their valence electrons are both in the same principal energy level, right? Let me go ahead and ink here. So you can see that I've identified that for calcium, it's in the 4s, and for bromine, it's in the 4s and 4p. And really just to solidify this fact, I've told us that they're, again, in the same principal energy level, okay? Now, given that we can kind of like get that out of the way, because that's what's in common with them, there has to be something different. And what's different is that bromine, because it has more protons, okay, it has a greater effective nuclear charge, okay? The reason we say effective nuclear charge is because, yes, you might talk about the fact that we have, the 4s that's filled, we have a couple, additional electrons there in the 4p level. And yeah, those additional electrons will provide a little bit more as far as like shielding effects goes, but we haven't increased the number of core electrons. So the shielding effects that have been kind of added just because we have the extra electrons there in the 4s and the 4p, really don't do that much, okay? It's the core electrons that we care about. So this is why we call it effective nuclear charge. We've essentially taken the number of protons and we've subtracted out kind of that slight, shielding effect there. So given that bromine has this greater effective nuclear charge, we're going to say that bromine therefore has a stronger attraction, right? Its nucleus has a stronger attraction for electrons. And when we're talking about electronegativity, we are talking about a pair of electrons when that atom is engaged in a covalent bond, okay? So that's kind of the progression there. What I want to do now is really get to some student responses, and let's kind of break these down. So in this first one, bromine is larger, okay, because than calcium because it has more energy levels. That is inaccurate. It does not have more energy levels. So that's the first thing that we said, that both of them have their valence electrons in the third principal energy level. Okay, I'm sorry, in the fourth principal energy level. So that's the first thing. We can kind of exclude that answer straight away. Okay, that's not the distinction between them. That's not the difference between them. In this next example, ZF increases the attractive force of the nucleus, this is true, and strengthens attractions of the electrons. Okay, that's not bad. What element are we talking about? Okay, so you need to get specific. You need to say that per the same principal energy level, okay, because again, um, those two elements, the potassium, is it potassium? I'm sorry, the calcium and the bromine have their valence electrons in the same principal energy level. So the difference is sure that they have, a different effective nuclear charge. That bromine has a significantly higher effective nuclear charge, um, but that is not explicitly stated. Okay, so you got to be specific in terms of what species that you are actually discussing. Um, let's talk about this next option here, or this next student response. Um, Bromine has a greater effective nuclear charge than calcium due to the greater amount of protons pulling orbitals in tighter. Okay, so far so good. Therefore, strengthening the attraction for electrons. That's not bad. That's not a bad response. That being said, I think what this answer is lacking is that, yes, you have a greater effective nuclear charge. And this matters because we were dealing with the exact same principal energy level, right? The valence electrons are on the exact same, fourth energy level. So let's establish what we have in common, and then let's differentiate between them based on the fact that, yeah, bromine has a greater effective nuclear charge. Okay. What this answer also fails to kind of talk about is that it's strengthening the attraction for electrons within a covalent bond. That's the true definition there of electronegativity. Okay. All right, let's push on to 3B. The ionization energy, really should say the ionization energy, sorry about that, of calcium is less than magnesium. Okay, so just kind of a quick recap. It's going to take less energy to remove an electron from calcium than it will from magnesium. So let's establish what we have in common, what we have maybe different. Um, Calcium has valence electrons in the 4s level. Okay, so calcium in the 4s, magnesium is over here in the 3s. So for calcium, its valence electrons are actually further away from the nucleus, right? They are in a higher principal energy level. Its N value is 4 as compared to an N value of 3 for magnesium. Therefore, okay, if we go back to Coulomb's law, where we have, the force of attraction is equal to K Q1 Q2 over R squared, or D squared. We're talking about the distance between charged particles. As we increase the distance, okay, say between this, positively charged nucleus and the electrons, and now the fourth energy level as opposed to the third, this is going to drive down that Coulombic attractive force. So subsequently, we're going to say that those electrons are less tightly bound. Okay, it reduces this Coulombic attractive force. Given that they're less tightly bound, less energy is needed to remove those electrons. Therefore, calcium has lower ionization energy. So I established what is different between the two elements. Okay, we talk about like what that really means, right? The fact that we have this higher principal energy level reduces Coulombic attractive forces. Therefore, electrons are less tightly bound. It requires less energy to be removed, and this is the definition of ionization energy. Okay, let's take a look at some student responses here. Magnesium has a stronger nuclear charge, making the attractive forces stronger. Therefore, the electrons are held more tightly in magnesium than in calcium. It's easier to remove an electron from the valence shell of calcium, resulting in a lower ionization energy. Okay, first off, when it comes to magnesium, as compared to calcium, um, magnesium has 12 protons, right? Calcium has 20 protons. So I would argue that calcium has a stronger nuclear charge. And you might say, well, calcium, is in the fourth energy level. So there's going to be more core electrons shielding those outer valence electrons. And thus, its effective nuclear charge is going to be diminished a little bit. And sure, but I suspect if we actually looked up those hard numbers, calcium is actually going to have a slightly higher effective nuclear charge. Okay. So you wouldn't go with that. Bottom line is, when we are talking about elements that are of different principal energy levels, where N is different, you have to invoke radius. Okay, you have to talk about the size of these atoms. You have to talk about the distance between the nucleus that has, your positive protons rather, and the distance between that and those valence electrons. Right? This might be what it looks like, say, for calcium, where that electron is out in the fourth energy level, but maybe for magnesium, maybe we have a situation that looks like this, right, where those electrons are a little bit closer. And again, we said that when that electron is further away, when that distance is increased, the Coulombic attractive force is diminished, easier to pluck the electron away. Okay, so I'm not sure that that response would get credit there. Let's take a look at this next response. The increased number of energy levels, N, in calcium relative to magnesium, so far so good, increases the distance over which the nucleus must pull, yes, and therefore reduces the Coulombic attraction for electrons. The last bit, the last little bit, this is missing, it's so close. Thus, it would require less energy to remove those electrons. That's the progression. What's different? What do we know as far as Coulombic attractive forces go, either based off of distance or effective nuclear charge? Okay, but in this case, we're moving up and down, so we're talking about a distance. And what does that really mean? Okay, it means it's going to take less energy to remove the electron, and that is why the ionization energy of calcium is going to be less than for magnesium. Okay, let's go ahead and talk about 3C. A lot of people had trouble here, okay? So the chloride ion is larger than the ion of potassium. The first thing I would do is I figure out what's going on with these ions, right? When chlorine becomes chloride and potassium becomes potassium ion, their valence shell both looks like this, right? That's what the last little bit of their electron configuration is going to look like. They now have the exact same electron configuration, okay? Which means we are talking about the exact same principal energy level, okay? So what must be different, if that's what's going to be in common, is that their effective nuclear charges have to be different. And we know that to be true, right? So for potassium, we know potassium has 19 protons, and for chlorine, that has 17 protons, okay? So the big difference here is that chlorine has less protons, therefore a smaller effective nuclear charge, okay? Now again, because we have a smaller effective nuclear charge, keep in mind that in the Coulomb's law kind of equation there, charge is in your numerator. If you have less, as far as like your charge goes, we're going to have a diminished attractive force, okay? That's what I say here, this weaker Coulombic attraction for electrons, which means the electrons are less tightly bound, okay? That electron cloud has the ability to kind of expand a little bit. And as a result, we said the ionic radius has been increased. A lot of people are talking about atomic size. I think it's more appropriate to talk about atomic radius, given that ionic radius, given that we are talking about ions. Okay, let's take a look at some student responses for 3C. Chloride is larger than potassium as a result of the added valence electrons of the chlorine atom, which creates increased repulsion between the electrons and an expanded electron cloud. If you're talking about chlorine versus chloride, yes, you nailed it. Chloride will be larger than chlorine because of this extra repulsion, okay? But that's not what we're doing. We're not comparing chloride versus chlorine. We're trying to compare chloride versus the potassium ion. And that's really what this question fails to attend to, okay? You have to make sure that we are comparing the ions, not the ion, to their individual neutral atoms, okay? Let's take a look at this next one. The chlorine ion is larger than the potassium ion because chlorine gained a valence electron, which caused the electron cloud to expand. So same kind of principle as the last answer. We have this, repulsive effects. While potassium lost a valence electron, making the ion smaller. Well, they have the exact same number of valence electrons, right? They have the exact same electron configuration, same principal energy level we're talking about. So what is the distinction? And the distinction is nuclear charge, right? A difference in that potassium has 2 more protons. So again, that is failing to address like the key why. Okay, this last response here, chloride gained another electron, sure. We're increasing electron repulsion, okay. Causing electron cloud to expand, absolutely. But again, you're making comparisons between, and she actually, or he explicitly says it in this example, you're comparing the ion to the neutral atom, and that's not what you want to be doing, right? Like you want to be comparing the ions to each other, because if we're going to say the potassium, right, is larger than chlorine, okay, and that's something we know, maybe potassium's larger than chlorine, but then all of a sudden chlorine actually became larger and potassium became smaller as they ionized. Now what's the relationship, right? So we have to make sure we are identifying what's in common and then ultimately what is the difference. All right, let's jump down then to the discussion of intermolecular forces. This is 5C. So we're given some data as far as boiling points for butanoic acid and then also decane, okay? We find that the boiling point, not much higher, but it is higher for decane. We're being asked to explain why. The first thing I want to point out is that while I think the Lewis structure for decane looks pretty good, okay? Butanoic acid, I would not award credit for this. In fact, when I scored your summatives, I did not, right? What we are failing to include are 2 lone pairs on each one of these hydrogens. And what I really like about the butanoic Lewis structure is that this carbon right here, it almost looks like, because we have those 3 electron domains, that sp2 hybridization, it actually accomplishes the trigonal planar structure pretty well, whereas for this second one here, the second oxygen here, given that now we have 4 electron domains, it's sp3 hybridized, that oxygen. The presence of the 2 lone pairs is going to give us a bent structure, and we're going to be looking at a bond angle of less than 109.5. But yeah, I like that geometry, that shape is actually almost provided there. All right, so let's jump into it. First things first, let's identify the polarity of these molecules. Again, we want to explicitly state what we know about these molecules. Okay, that's got to be the first step. What do they have in common? What is different about them? And then we delineate from there. So for butanoic acid, if we go back to the structure, that is a polar molecule. That carboxyl group on the right side of the molecule, super polar, okay? Obviously, every single molecule is London dispersion forces. The fact that we have this, polar group is going to make it a polar molecule. So we have, a area that's going to be, partially negative, partially positive. So we have dipole-dipole intermolecular attractive forces between separate neighboring butanoic acid molecules. And finally, we have hydrogen bonding, which can often be a very, very strong, the kind of preeminent intermolecular attractive force. That's what's going on for butanoic acid, okay? As far as decane goes, we have a nonpolar molecule, and it is limited to just London dispersion forces, okay? Now, we have to find a way to reconcile the fact that decane, which appears to have weaker intermolecular forces, actually has a higher boiling point. So we know, given the data, that decane actually has stronger intermolecular forces. So how do we justify that, right? Well, what we do is we have to really dig into what's going on with these dispersion forces. And so for decane, this is an enormous molecule, right? We got, what was it? It was C10, H22. So a lot of carbons, okay? Which means we have this enormous electron cloud, right? And then the shape of the molecule, given that we're talking about N-decane, that just means that it's like linear. We don't have really any like branching or anything. Really large surface area per volume, which means as far as dispersion forces go, it can make kind of a lot of, intermolecular kind of attractive type connections with other decane molecules. So that's a super polarizable molecule, okay? If it's really polarizable, this means that those London dispersion forces are particularly strong. So what we would say is that these really strong intermolecular attractive forces between, not within, but between separate neighboring decane molecules, this is really strong. And subsequently, it's going to take a lot of energy to overcome those intermolecular attractive forces and spatially separate them enough such that we can transition from the liquid to the gaseous state. And if you require a lot of kinetic energy to do this, we're going to say that decane then obviously has a higher boiling point. Okay, so we start again by identifying what is in common, what is different, and then we justify the data using what we know to be true about this concept of polarizability, size of electron cloud, and how that manifests in greater London dispersion forces. Okay, let's take a look at some student responses. Decane has a higher boiling point because it has a larger electron cloud. Awesome. Okay, which means it's more polarizable, on the right track, which makes it harder to break bonds right here. This is problematic. we are not breaking bonds, okay? When we undergo a phase change to go from the from the liquid to the gaseous state, if here's a liquid molecule, liquid molecule, liquid molecule, liquid molecule, liquid molecule, what we're doing is we are separating them, okay? We are not inherently breaking the bonds within them. We're just separating them out. And formerly, this might get a little crowded here. I'll draw a little, like, these are not bonds, right? These are intermolecular attractive forces. And to go from the liquid to the gaseous state, we need to completely overcome those, okay? So again, we are not breaking bonds. We are overcoming intermolecular attractive forces. Um, right from the get-go, I would argue, where is the analysis between these molecules? We've not identified what's polar, what's non-polar, what they individually have as far as their own independent intermolecular attractive forces. Let's move on. Decane has a higher boiling point, okay, than butanoic acid. Because decane has a longer carbon chain than butanoic acid, so it requires more energy to break the butanoic acid. Again, this concept of breaking, we're not breaking the carbon chain, okay? Now, yeah, it's a really large molecule, but what does that mean in terms of intermolecular attractive forces? If it's an enormous molecule, then we need to talk about the fact that we have this enormous electron cloud, right? That we can have, this disparity in electron distribution where we can have, this asymmetric distribution where we have a really, really large partial negative, really, really large partial positive that just kind of instantaneously, rises. But that's not captured by saying longer carbon chain. You would really have to say, again, larger electron cloud. And you'd have to address surface area, but it's this broken that I'm particularly not fond of there. Two more. Decane has a larger electron cloud, is more polarizable, making its LDF stronger than the LDFs, dipole-dipole, and hydrogen bonding forces in butanoic acid. This is a great answer. This is a great answer. So why would this not receive credit? What does this mean? Okay. Like, just because the intermolecular attractive forces are cumulatively stronger, and I like that, the fact that they are listing the others and they're basically saying it's larger than the combined, IMFs of the butanoic acid. What does that really mean? That means it requires more energy to separate, right? More kinetic energy, which means when we talk about kinetic energy, we're talking about monitoring that via temperature. That's why we have a larger boiling point. So it fails to really put that nail in the coffin, that last little bit. Stronger IMFs, like the London dispersion forces, are than the cumulative IMFs of the butanoic acid. Thus, it requires more energy, which is why we say it has a larger boiling point. Okay, so we failed in that aspect there. Last example, I believe. Decane is more polarizable than butanoic acid. Great. LDFs increase with increased polarizability. Awesome. Stronger LDFs of decane make its boiling point higher than that of butanoic acid. This is terrific. This is a great delineation, but it's only addressing what is going on with decane. You got to start your responses by talking about decane versus butanoic acid. Okay, so it's the same kind of idea. So we didn't do kind of the independent analyses, and then we also didn't say that we require more energy. Okay, whenever we're talking about solid to liquid, liquid to gas, we have to be talking about more energy. That's required to overcome those IMFs. And going from solid to liquid, we're overcoming a fair number of intermolecular forces. But when we go from liquid to gas, that's where we're overcoming literally all of them, right? We're assuming that in the gaseous state that IMFs are negligible, that we've almost completely minimized or overcome those. All right, thanks for tuning in, guys. All right, bye.